couple of minutes to go, but I know I'm keeping you all from morning tea today. So it gives me great pleasure to introduce Chiara Pisapia, who is today presenting her pre-completion seminar, which is one of the final hurdles in her PhD. Chiara came to JCU in 2010 after doing a master, her undergraduate and master's at Rome in Italy. For her master, she was looking at the effects of sedimentation on colonies, coral colonies in Indonesia. She then came to JCU and did a minor project with myself and Andrew Cole, looking at the effects of butterfly fish in delaying recovery of corals from bleaching, and then went on to do a PhD. So she started on the master and upgraded to a PhD in 2012. The focus of her PhD, as most of her previous research, is looking at the responses of corals at the level of colonies to different disturbances. Thank you.
Thank you so much, Morgan, and thank you all for coming. So we all know that coral reefs are a highly dynamic ecosystem, naturally subject to a wide range of disturbances operating at different spatial and temporal scale, ranging from mass bleaching event to more chronic localized removal of live tissue. However, the increasing effect of global climate change, together with more direct anthropogenic disturbances, they are causing an increase in the rates of coral loss beyond those which can be sustained, and also the capacity of corals to recover between those disturbances might be declining. This is just an example from the Great Barrier Reef, and we have the coral cover and time, and we can see a steady decline in coral cover on the Great Barrier Reef. But what we're missing is the chronic disturbances, because it's not just the acute disturbances. Chronic disturbances, they contribute to reef degradation and they undermine the capacity of coral to recover from acute disturbances. While the acute disturbances, they might direct kill the organism and change the community structure, we need to remember that also chronic are important because they can affect the rate and trajectory of recovery. And it's not just the acute disturbances that are increasing, it's also the chronic. We all know that sedimentation rates are going to increase, and we all know about ocean acidification. So calcification decline with declining pH. And that is how they already show that corallis is growing slower. Here we have the calcification, and we can see a decline through time. However, coral, they can still recover after major disturbances, and recover can happen or through the regrowth of remnant corals and or through the settlement and then subsequent growth of new recruit. And usually, as you might think, the recovery is faster through the regrowth of remnant corals. And here we have two examples, one from the Great Barrier Reef and one from Scott Reef in the Indian Ocean. And we can see that once it happens, recovery is relatively fast. And this is because coral cover never dropped below zero. So the recovery actually happened through the growth of remnant corals. We all know that corals are modular organisms, so they're made up of repeated building models that can function as physiologically independent units. So corals can survive extensive injuries on a scale far beyond the regenerative capacity of most solitary organisms. However, partial mortality results in a decline in the number of total polyps that make up a colony. So this can affect, not reduce the size, and can affect the fitness of corals. Because we know that in corals, reproduction, mortality, survivorship, growth, they're all strongly site-specific. For example, look here, we have colony fecundity, and we can see that it increased with size. And we know that big colonies, they will produce more eggs for surface area, so they will have a disproportionate role in recovery. But partial mortality will cause a decline in size. And it's not just the fecundity. If we look at the probability of whole colony mortality as well, it declines with size, while the chance of survival, they increase. And when we look at partial mortality, well, we can see that it tends to increase with size. This is because imagine an injury on a small colony. Well, it's more likely to result in whole colony mortality, while on a bigger colony, some portion might still be alive. And also, bigger colony might be older, so injury can accumulate through time. However, when colony have partial mortality, they not only reduce size. A colony with high rates of partial mortality will have to divert limited energy towards repairing damaged tissue. So less energy will be available for growth, reproduction, competition, and other metabolic process. So this colony with high rates of partial mortality, they might be more susceptible and less able to recover from acute disturbances. And most importantly, on the reef, there are no periods free of major disturbances. If we look here, both Wakeford and Medin, they show relatively high rates of whole colony mortality. We're talking about 15%. In period, they are supposed to be free of major disturbances. For example, no cyclone, no bleaching event, no crown of thorn outbreaks. But we still see relatively high level of mortality. This is because even in absence of major disturbances, coral are still subject to a wide range of chronic, often small-scale disturbances that can still cause relatively high rates of mortality. And these disturbances, they might be, for example, predation, competition, disease. They are natural, they are part of the natural dynamics and turnover of population. But if they're high, they can reduce the capacity of corals to recover between major disturbances. And here we can see that proportion of injured colony in period free of disturbances is more than 60%. So we know that background partial mortality is high and it's important, but does it actually vary spatially? Because if it does, this can result in spatial variation in population dynamics. And Hughes et al., they inferred that there must be underlying variation in the growth of corals along the Great Barrier Reef, but this has never been tested. And here we have the recruits and adult abundance in the northern Great Barrier Reef, Lizard Island, in the central Trunk Reef, and in the south Heron Island. And we can clearly see that the adult abundance is relatively homogeneous, despite differences in recruits. And the lack of conformity between adults and recruits suggests that there might be underlying variation in post-recruitment process, but we don't really know this. So the overarching aim of my PhD was to investigate the ecological role of background partial mortality. But let me explain a little bit better what I mean. So first of all, we wanted to investigate whether there are spatial variation in background partial mortality. And second, we wanted to investigate the ecological response of the corals to partial mortality. So to answer the first part of the PhD, we investigate prevalence and severity of partial mortality. But let me explain. When we talk about prevalence, we are looking at the proportion of injured colonies versus uninjured per site. So we are looking at population level. While when we talk about severity, we are looking at the extent of dead tissue versus live tissue per colony. So we're looking at individual level. So the first step was to investigate prevalence and severity of partial mortality at the hierarchospatial scale on the Great Barrier Reef. And we did this only based at the beginning on instantaneous measurement of observable injuries. So I went on the reef, saw a coral, and assessed the partial mortality. But then we went back on the same exact colony and we investigate the prevalence and severity of partial mortality of the same exact colonies, but with repeated measurements, so through time. And we did this especially because we wanted to investigate whether extent of injury can affect the growth of the corals. And then, since we weren't happy, we also look at we compare the prevalence and severity on the Great Barrier Reef with the Maldives in the Indian Ocean. So after we investigate spatial variation in tissue loss, the next step was to better investigate what are the effects of partial mortality on colony condition. So first of all, we wanted to investigate the influence of injury. But in this case, when I talk about injury, I'm not only talking about observable injuries that we can see, but also not observable. For example, if we think of feeding by butterfly fish, they do not leave a sign on the corals, but they still impair an energetic cost on the corals. But we don't really know. So, and also, the second step was to investigate the energetic consequences of tissue repair. But when I talk about energetic consequences, I'm not talking about how much energy go to regeneration. I'm talking about decline in the physiological condition of the corals. They are associated with an increasing energy expenditure on tissue repair. So let's start with the spatial variation in partial mortality. So we investigated prevalence and severity. Remember, prevalence, proportion of injured colonies, while severity is the extent of that tissue. And we did this at a hierarchy of spatial scale. So at the largest scale, we have 3 latitudinal sectors, one in the north in the proximity of Lizard Island, one in the central in the proximity of Trunk Reef, and one in the south in the proximity of Heron Island. And I'm sure you're all familiar with these sites. In each sector, then we had 3 mid-shelf reefs. In each reef, we had 3 sites. And in each site, we had 3 consecutive transects. And along each transect, we recorded all living colonies of these 4 major taxa. So encrusting Montipora, branching Pocillopora, massive poritis, and Acroporitis intres. And we choose those taxa because, as you can see here, they are the most abundant at the study site, and also they have contrasting morphologies and life history strategies, which result also in contrasting susceptibility to agent of partial mortality and regenerative capacity. So along each transect, we recorded the position of each colony relative to the permanent transect, here in the black box. And then we took a picture and we recorded the aerial extent of injury, and it ranged from 0 to 100. And it was calculated to the nearest 5%. So we surveyed 2,276 colonies along the Great Barrier Reef. And let's see what we found. Okay, here we look at the proportion of injuries. So remember, we are at the population level. Here we have the 4 different taxa, and we have the 3 different sectors. And the first thing I want you to look is that we have high prevalence of injury. For example, look at Montipora and Poritis. Almost all the survey colonies are injured. And similarly, also in Hyacinthus, we have almost 80% that the colonies are injured. But let's look at severity. Remember, I showed you this graph before, so we have adult and recruit abundant. So if you guys look at this graph, you would agree with me that you would expect to see higher partial mortality in the north, in Lizard Island. But let's see what we found. Here again, we have the extent of injury, and we have the 4 different taxa in the 3 different sectors. Well, you can see that actually we do not see higher partial mortality in the north, and most of all, we don't see a clear trend. For example, here we could see a higher severity of injury in the south, and this might be for latitudinal variation in environmental variables. For example, temperature and light, they might be declined with latitude, and they have been shown to affect regeneration. So corals in colder water, they regenerate slower. So this could be an explanation. But let's have a closer look at the variance component to better understand why we do not see very significant differences between latitudinal sectors. Well, if we look here, we have again the 4 sectors, the 4 taxa. We can see that most of the variation is explained by the error, which means that the greatest variation is between adjacent colonies within the same reef habitat. So there is more variation between 2 colonies sitting one next to each other than there is between 2 colonies in different latitudinal sectors. And this is really interesting. And it tells us, first of all, that the process that injure colonies are very localized. and that might vary from damage from fish to microorganisms to bioerosion to damage from sand and waves. But also, more importantly, this tells us that the disturbance history between adjacent colonies is highly variable, and it might be more variable than it is between disparate populations. And also, the susceptibility of corals and their capacity to recover from acute disturbances may be highly variable at this local scale. So, for example, the variation between those two colonies is greater than there is between this colony here and one sitting up at Lizard Island or one at Heron Island. And this is really interesting. And when we look at size, remember I told you that partial mortality is supposed to increase with size. So according to this hypothesis, you agree with me that you would expect that higher partial mortality will be found in bigger colony. But when we look at the data, here we have the percentage of colony, and here we have the colony size. We have the 4 different taxa, and here we have the percentage of partial mortality in all size categories. When I talk about, like, for example, a colony in this size category, it would be a colony with like 10 centimeters diameters, while a colony in this size categories might be 30, 35 centimeter diameters. And when you look at this graph, you agree with me that we do not see higher partial mortality in bigger colonies. But remember I told you that this what I showed you are based on instantaneous measurement of observable injuries, which are really important, but they can only provide a snapshot because they only allow us to capture recent mortality. But we all know that injuries regenerate with different rates. So for example, an injury that do not regenerate at the beginning can start regenerating later, or vice versa. But this would be missed if we only measure instantaneous measurement of injuries. And also, injuries are not usually isolated events, but they're more chronic repeated events. But again, we will miss this if we don't repeatedly sample the same colony. And most of all, when we resample the same exact colony through time, we can also account for variation in the growth, so the effect of partial mortality on growth. So importantly was to combine the instantaneous measurement with repeated measurement to have a better insight in the temporal dynamic of injury and to better understand the ecological significance. So we went back to sample the same exact colony. Remember I showed you we have the 3 different sectors, so in the northern Lizard Island, trunk reef in the central, and in the south. We have again the 3 reefs for each sector. We have 3 sites and 3 transects. But this time we also have time. So we have the first year, second year, and third year. And clearly we resample the same exact colonies, so the same taxa, so again Acropora hyacinthus, branching Posilopora, encrusting Notipora, and Massiporitis. And let's see what we found. Let's look at the proportion of injured colonies. So remember prevalence of injury, population level, and here we have the 3 different sectors. We have the 4 taxa, and we have the 3 years. Well, we can see that again, prevalence of injury is extremely high. If you look at Poritis or Montipora, again, we see that almost all the survey colonies are injured. And also, prevalence of injury seems to be constant through time, except in Poritis Heron. And when we look at the severity, here again we have the 4 different taxa with the 3 year, and we have the 3 sector. Well, we can see that injury seems to be fairly constant, not dynamic. So a colony in year 1 has the same extent of injury after 2 years. And interesting, I want you to look at that Poritis and Montipora seem to have higher partial mortality than fast-growing corals like Hyacinthus and Posilopora. These, if we look carefully, these reflect also differences in investment in repair and growth. So, for example, Poritis is an slow-growing, long-living corals with long generation span, while Acropora is a fast-growing corals with great regenerative capacity and short lifespan. So it's possible that Hyacinthus has high rates of wall colony mortality and high rates of regeneration, so this results in less observable injury. And during this study, we did not have any major acute events. So this mortality that we're looking here is based on background chronic disturbances. So, and I wanted to mention that, again, similar with the instantaneous measurement of injuries, we do not find a significant difference between latitudes. But again, the greatest variation is between adjacent colonies within the same reef habitat. And when we look at the size, well, here we have the percentage of variation in size, here we have the extent of injury, and we have the 4 different taxa. Well, we were expecting a relationship of this kind, where we have negative growth with increasing partial mortality. But this is not what we actually found. And we need to remember that there is interspecific variation in the growth of individual corals. And also, what we measure in this study is only observable injuries. So remember I told you that there are also not observable injuries that can have still an effect on the physiological condition of the colonies. So we saw that the greatest variation is at a very small spatial scale, but what happened if we increase this spatial scale? So is it greater variation between 2 colonies sitting one next to each other than there is between colonies in different geographic locations? Because we need to remember that chronic disturbances, they might vary from millimeters to thousands and thousands of kilometers, and this can result in greater difference in tissue loss. So in order to answer this question, we compare prevalence and severity of injury in corals in Lizard Island in the northern Great Barrier Reef and in Laviani Atoll in the Maldives. And we have a similar sampling design. So we have 2 geographic locations. In each location we have 3 reefs, and in each reef we have 3 sites, and in each site we had 3 consecutive transects. And again, we saw the exact same coral taxa, so Acropora hyacinthus, massive poritis, branching Posillopora, and encrusting Montipora. But let's see what we found. Here we have prevalence of injury. So remember, population level and its proportion of injuries. We have the 4 different taxa, and we have the 2 different locations. And first of all, again, we have high prevalence of injury. Again, almost all the survey colonies in poritis are injured. And you can clearly see that there is not a great difference between these 2 locations. And when we look at the severity, again, we have the 4 species and the 2 locations. Well, again, we do not see a clear differences between the Great Barrier Reef and the Maldives, actually, Lizard Island and Laviani Atoll. But let's look at the variance component again. Well, we understand why, because again, similar that we saw before for the Great Barrier Reef, this greatest variation is again between colonies that are within the same reef habitat rather than between different geographic locations. And now that I've showed you differences in, we found very interesting actually that we did not see any large-scale differences between the Maldives and the Great Barrier Reef, despite great differences between the ecosystem state. And now that I've shown you that there is spatial variation in tissue loss, if we want to understand what are the causes of partial mortality, well, the specific drivers remain unclear. Because look at this picture. Could you actually tell me what is the specific driver of that injury? Well, I don't think so, because partial mortality is the general stress response. So it's really hard to pin down the exact cause unless repeated sampling occurs very frequently or the causative agent is clearly distinguishable, for example, grazing by parrotfish. So in that case it would be easier, but otherwise it's really hard to tell the specific causes of partial mortality. So we saw that there are spatial variation in tissue loss. Now, the next step is to investigate the ecological consequences of injuries. And we'll start looking at the influence of injury on colony condition. And remember, when we talk about injury, we're talking about both observable and not observable injuries. So, for example, feeding by butterfly fish. So in order to answer this question, we surveyed 24 colonies of Acropora spatialata and 24 of Pocillopora damicornis from the same reef habitat Elizardinum, and we repeated sampled these colonies to investigate intraspecific variation in physiological conditions driven by different chronic disturbances. So we investigated predation and partial mortality as major drivers, and also we wanted to account for other factors that can cause variation among colonies. So we also look at distance of colonies from the crest and competitive regime. And for partial mortality, again, we measure the extent of injury. So again, from 0 to 100% amount of dead tissue versus live tissue. And with predation, we recorded every colony with a GoPro for 1 hour, and then we recorded the total number of bites per colony taken by all corallivores. And before you guys look at this graph, I want you to remind that when we talk about physiological condition, we measure the total lipid content and the zooxanthellae density, because those two are good proxy of coral health, and they've both been shown to vary with changes in environmental conditions. This is a simplified model of a multiple regression where we tested the two different species and we tested the effect of these drivers on the physiological condition of the colonies. And we can clearly see that we do not see any effect on Pocillopora damicornis, but we do see the effect of partial mortality on colony conditions. So it causes a decline in zooxanthellae density, while distance from crest causes an increase in the lipid and the zooxanthellae. But let's have a closer look at what happened to the physiological condition of the colonies with time. So here we have zooxanthellae density and the total lipid content for the two different species, and we have the two different sampling months. We can see that zooxanthellae density does not change through time, while when we look at the total lipid content, well, we can see that in both species we have a significant decline with time. And this could be in part to background mortality and in part to a limited productivity with winter, so declining temperature and light regimes. But let's have a closer look at what actually happened to the drivers of variation. So here we have competition and partial mortality and predation. Again, we have the two different species and the two different times, and we can see that competition and partial mortality are fairly constant through time. While when we look at predation, we see a very significant increase in predation rates on damicornis. And the rates is around between 0 and 100 bites per colony per hour. And very interesting, these colonies that received moss bite in May were not the same that received the moss bite in October in both species. So we saw effect, the influence of injury on colon condition, but let's look at the energetic consequences on tissue repair. And remember, when we talk about energetic consequences, we're talking about decline in physiological condition associated with an increase in energetic expenditure on tissue repair. So in order to answer this question, we surveyed, one major point that I wanted to make. We know that there are interspecific differences in regeneration rates. So for example, look at percentage of injury regeneration here over 71 days. Well, we can see that Acropora robusta fully regenerates the injury, while Acropora peripera doesn't even start regenerating. So we know that there are interspecific differences. But what are the energetic consequences of physiological condition on these interspecific differences? Well, we don't know. And they're likely to be very important in understanding differences in susceptibility of these corals to acute disturbances and their subsequent capacity to withstand and recover. So, okay, now I can tell you that we surveyed colonies, again, from Acropora spatulata and Posilopora damicornis, from the same reef habitat, the reef crest and desert island, and we repeatedly sample these colonies. We sample them in March when we injure them, then we resample them in April and then in September. In March, we experimentally cause injury, tissue loss, so we remove tissue from the colonies, and we cause 2 injuries that together accounted for 10% partial mortality. And let's see what happened through time. And again, when we talk about physiological condition, we measure zooxanthellae density and total lipid content. So here we have the 2 different species, and we have the zooxanthellae density in the different months. And we can see that zooxanthellae density are fairly constant through time. But let's see what happens to the lipid. Well, again, we have the 2 different species and time, and again, we see that lipids in relative is constant. It doesn't decline with time, and we were actually expecting to see a decline in total lipid content in September. But let's have a closer look at partial mortality. Well, here again we have the 2 different species, and we have in April after the 1 month after the injury, and in September. Well, you can see that partial mortality does not change, and this is not what we were expecting. We were expecting to see a decline in partial mortality and an increase in total lipid content, but this is not what happened. So these colonies, they did not regenerate. So we can see here we have the same exact colony in March, just after the injury, and then in September. And we can see that we have algae. So the colonies did not regenerate, and very interesting. I told you that we injured 48 colonies, so 24 of one species and 24 of the others. Well, in September, 7 were dead. So the colonies that did not, some did not regenerate and some even died. So as an overall conclusion on this beautiful PhD, we can see that background partial mortality is high and is constant in all location and latitude, but is highly variable among individual colonies. So this suggests that colonies with high partial mortality might be in poor physiological condition. So they might be less able to withstand, survive, and recover from acute disturbances, comparing to conspecific with less partial mortality and probably in better physiological condition. So as thesis outcome, we have 2 chapters are published. One is in review, one will be submitted shortly, and one is in preparation, while those are other publications that are not related with the thesis. Okay, first of all, I would like to thank Morgan and Hughes. They are amazing, and a special thank to Morgan. I could not have asked for a better supervisor. And a thank you, the big one, also to the Center and Ames GSU. They've been amazing. And also thank you to the funding bodies and the research station. Thank you to all these beautiful people, especially Kristen, because she knows how hard it is to resurvey the same exact colony on the Great Barrier Reef. And a special thank to all of you for coming. Thank you.
Questions? Questions?
The last bit where you showed physiological responses to injury, lipids, and susceptibility, those graphs didn't have control trends.
Which one? Sorry, there.
About 3 of them. Yeah, that's one. That's another.
Those ones?
Another. Yeah. So, is that just seasonal variation, or have you got a control treatment?
Those colonies are the same one that we measured before, in the other study that I showed you, and does not change with time.
Yeah.
Like because we injure all the colonies and then we measure this. And when we tested their effect to see if it was actually injury causing declining zooxanthellae rather than, for example, daylight, we do not find any effect. Where it is? Oh, it's in the other. Hold on, let me go back.
but my point is you've shown one treatment there, which is the injured corals, and
yes.
decline from the first census to the second, but perhaps uninjured corals do the same thing.
And yes, I agree with you, and that's why before we followed those colonies in 2012, in May and in October, and this is what I showed you. And then I went back in 2013, 1 year later, in March, and we injured them. So those are the exact same colonies.
Right. So you have that data on the same graph.
Okay, so that's why we did not have different treatment. But some unfortunately died, but they were the same exact colony.
Yeah, well, you'd expect some to die. They don't live forever.
Yeah, yeah, but when you are testing them, the physiological condition, you want them alive. But
Chiara, why did you use zooxanthellae density? Why not also do chlorophyll concentration? Because the chlorophyll concentration can change in any single zooxanthellae, depending on what time of year it is.
Actually, we were looking at variables that changes with environmental time, with environmental variable, and we thought that would be easier to investigate zooxanthellae, the whole zooxanthellae, rather than the chlorophyll. And also for logistic reason, for time-wise, I already knew how to do it. So we thought that being confident on doing it, it would be best. But I agree, definitely, the chlorophyll is another important variable. And also with the lipid, people might argue that why you didn't look at protein and carbohydrates, for example. But for the lipids, we have that they have more energy for unit weight. So there are other variables, I agree with you, that vary with environmental condition, but we measure those too, because they have been shown to vary as well.
Why did you choose May and October? I mean, what were the reasons for your sampling?
It was, first, we wanted to look, for example, at winter and summer, and also for logistic reason, because with those colonies, some of these were only exposed reef crust, and during the winter, it's very windy, so we decided to do after, to have the first one in May, so beginning of winter, and the second one at the beginning of summer. For example, if there were any variation during winter, if we measure it in December, we would miss it, while if we measure at the beginning of summer, we would see it. That was the main reason. Yes?
You invoked Hughes et al. 99, thank you very much. But I think you've misinterpreted what it actually said. So you two graphs that you said came from that paper?
Hold on, yes.
They actually don't.
No, I remade those.
Okay.
I didn't steal them, I just stole your data. Remade the graph.
Well, it's misleading to have a graph and say Hughes et al. Underneath it. There was another one that was...
It's the same graph.
Okay. We actually looked at 33 reefs.
Yes.
And so the data for individual reefs, I guess Morgan gave you because he was part of the team that collected it. What's the y-axis? Because I don't recognize it.
It's the abundance of adult and...
percent cover of adults?
Yeah.
Go ahead. And
so
what about the recruits?
I know that your paper tells another story, but I use your data to justify my story.
Okay, but I'm trying to figure out what you're saying. Yeah. So is that number for the recruits? Is that number of recruits?
I think it was the number of individuals, and I think I averaged it for. I think for the recruits were per panel and the adult per site, and then I only stole the sector that I needed. But you measured the latitudinal differences on the group. There were more sectors, but I only focused on the two that I needed.
Yeah, well, a couple of points. One is, I'm not sure it's valid to represent a sector of the barrier reef with data just from a single reef. And even within a reef, you should really have error bars on all those 6 bars to indicate what sort of variation was there. So in our paper, we didn't actually present absolute cover or absolute density of individual reefs. So that's a sort of derived graph. And you made some statement about an inference was that mortality would vary latitudinally.
No, because from my point of view, so if here there is...
No, you had a word slide that said the inference is mortality varies latitudinally or something.
No, what I was saying is that the growth, variation in the growth of the corals might vary. Because here we have great differences between adult and recruits.
But that statement attributed to our Nature paper, we didn't actually state. So that's your interpretation.
Yes.
I'm just making the point that the graph doesn't come from our paper, and the statement, we didn't actually make that inference.
No,
That's your interpretation of
yes,
the paper.
Yes,
Which,
yes.
Which I wouldn't have made.
Yes.
Okay, that's all I'm saying.
No, yes. I extrapolate the data from your paper to justify why I would go and look along the Great Barrier Reef. Because reading from your paper, we saw that there were differences between adult and recruit. So we thought, okay, maybe those differences might be due
The
to
reason I'm
post-recruitment
confused is
process.
that in our paper, our y-axis was the amount of overall variation, which was explained by different scales, sector, reef, site, within site. So we didn't have a graph like that in our paper. That's why I'm confused.
Yes, no, exactly. I remade it. Like, this is not from your paper. I used the data from your paper. That's why I cited you, because it's your data. But I remade this graph to show why I went along the Great Barrier Reef.
Yeah, well, you used 10% of the data, because that's the rate.
Yes.
Any other questions?